Hello, math students. Welcome back to our module on statistics. This is lesson 3, and it is called The Mean as a Balance Point. And our goal for this lesson is today we will learn how to use the mean as a balance point to compare all other data points of the data set. And so figuring out the mean is kind of really important. The mean, if you remember from yesterday's lesson, is the mean is the fair share. What is the amount that all of the data point holders share? Okay, so that's the mean. That's the average amount, the mean amount. And so when we're using it as a balance point, we're literally thinking of like a teeter-totter, so that instead of it flipping on one side or flipping on the other side like a teeter-totter does, we actually want it to be balanced. We want it to be equally even on both sides. And so today we will learn how to use the mean as the balance point to compare all other data points of the data set. The question that I want you to think about in this lesson is, how do you compare a data point to the mean? What does the comparison tell you? Okay, so on things to remember, we're building every day in our knowledge about this statistics stuff, and the mean is a value that shows that every data point is equally distanced away from. Okay, so the mean is the fair share amount of the data, and then what you're trying to do with that mean today is you're trying to figure out what is the distance away from the mean to every point on your graph. So this, if you ignore the triangle for just a minute, this is just a regular old dot plot. Okay, so we have a dot plot right here. Our dot plot says we have 1, 1, we have 1, 4, we have 2, 5, we have a 7, we have an 8, and we have 3 11s. So if we were to equally disperse them, fair share them out so that each person has the same amount, what we would determine is we would determine that 7 would be the equal amount. Now, I also want to cover something very quickly because we need to make a transition in the fact that in order to find the mean, you don't have to draw the boxes to do the fair share. What you can actually do instead of drawing the boxes, now that we know what fair share means, is you just write down what you have. And so we have 1, 1, we have 1, 4, we have 2, 5, so you're going to do 5 and 5 because there's 2 of them. You have 1, 7, you have 1, 8, and you have 3 11s. So what you do with this information to figure out what the mean is, or the fair share, is you actually add them all together. So we're going to start right here. So 1 plus 4 is 5, 10, 15, 8 and 7 is 15 again. So that's 30, 31, 32, 33. And then we put that one up here, 3, 4, 5, 6. So we have a total number of 63. And then we divide that number, 63, by how many are represented. So we have 1, 2, 3, 4, 5, 6. So what I did is I just literally counted how many have dots on them. And that would be how you're determining that. So if we count that, 1, 2, 3, 4, 5, 6, 7, 8, 9. I apologize. You don't count the number. You count the dots that you have. So we take that. So count our dots. 1, 2, 3, 4, 5, 6, 7, 8, 9. That means 9 kids were interviewed. That's what you do. You have to count your numbers that are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Come on, Mrs. Nelson, think about it. So 63 divided by 9 is 7. And 7 is your mean. Okay? So if we fair shared it, we would see that 9 kids get 7 boxes above them. Okay? When we fair shared it out. So without having to draw your boxes for your fair share, again, what you do is you write down what you have, 1, 1, 1, 4, 2, 5, 1, 7, 1, 8, and 3 11s, which means that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 kids surveyed. That's where the 9 comes from. Add all of your amounts together and then divide it by the 9 kids, and equally fair sharing, or mean, would be 7. Okay, so that's how you find the mean in order to do it without the fair share boxes. Okay, so now getting back to figuring out what it means to have a mean as a balance point is we draw on our dot plot an arrow that sits under the mean. And it could sit above the mean or it sits under the mean. According to this, we're having it be under it this time. And the reason why you draw the arrow is because the arrow tells our eyes this is what you're comparing. So the arrow is what you compare every dot to. So if we're looking at it and we're comparing 8 to 7, we know that it's 1 hop away. So that's a 1. And then we compare the next one all the way over to here, we see that it is 1, 2, 3, 4 hops away. So that's 4 hops away. Then the next data point is 4 hops away. And the third data point is 4 hops away. So you're literally counting the hops from each data point. So now let's go on the other side. So to go from the mean to this dot, you're going 2 hops away. So that's where that 2 comes from. To go from the mean to this dot, you're going 2 hops away. To go from the mean to this dot, you're going 3 hops. Count them, 1, 2, 3 hops away. And to go from this dot all the way over to this dot, you're going to go 1, 2, 3, 4, 5, 6 hops away. So this little chart down here tells you the number of hops to the next data point. And it says distances to the left means a total of 13 units to the left. Distance to the right means that there are a total of 13 units to the right. Now, all of you are thinking, how did they get 13? Well, the way that we got 13 is we counted them. So count them all together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 spaces away from the mean on the left. Okay, now let's go this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spaces to the right for each one of those data sets. So these numbers are very important because what they're telling you is how many hops or what the distance is from your mean. Okay, and so that's how we know using the mean as the balance point what the distances are. Okay, so then the next thing that we have to figure out is we have to figure out the deviation. The deviation, boys and girls, is actually the distance from the data point to the mean. So all of these down here are called deviations. What you can call them is deviations. Not hops, but deviations. Deviations means how much does it change from your mean. So our mean on this example is 5. So what we're missing on here is we need to draw our box because that's our mean, right? So you draw your box on your mean, and then you determine the deviations or distances. So it's another word for distance, deviations from the mean. So if this first dot is 1 deviation to the left, so we're calling it a negative because you're going backwards on your space. Okay, this next one, this next dot is a whole and a half, so a negative 1.5. This one is 2 full hops from 5 to 3, and we have 2 of them, so 2 full hops from 5 to 3, so those are both negative 2. And then this guy, to go that way, you go 1, 2, 3. So it's 3 whole hops to the left, which gives you a negative 3. So negative 3 deviations from the mean, negative 2 deviations from the mean, negative 2 deviations from the mean, negative 1.5 deviations from the mean, and negative 1 deviation from the mean. The negative is just telling you you're going below the mean. The positive means you're going above the mean. So if we look on this side, we have a positive 1.5 because here's 1 whole and then half, so 1.5. 2 wholes would be here, and then 1, 2, 3 would be this one. 1, 2, 3 would be this one. And so that's how you find the deviations. So the deviations are just like up here. They were calling them distances. Now they're called deviations because that means how far away from the mean did it go? How far did they deviate? How far did they veer? How far did they change from the mean? So that's what a deviation is, okay? When you're calling them a deviation, if the distance is below the mean, they're negative. If it's above the mean, it's positive, okay? All right, so that was good to help us figure out what would the total deviations be on this side. We'd have 3, 4, 5, 6, 7, 8, 9.5. So it would be negative 9.5 deviations on this side, whereas on this one, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9.5. So this would be positive 9.5 on this side for the deviations. All right, so it says the mean is the balance point because the distance from the balance point, a data point, and its opposite is always equal distances. So let's go back and look at that for a minute. How many to the left did we go? 13. How many to the right did we go? 13. How many negatives did we have on this side? Negative 9.5. How many positives did we have on this side? 9.5. And so what you can see is they are the exact same distances because you would always take the absolute value to determine distances. The absolute value of negative 9.5 is 9.5. The absolute value of negative 9.5 or positive 9.5 is 9.5. And so they are balanced. 13, 13, 9.5, 9.5. And so the mean is the balance point because the distance from the balance point to all of the data points and its opposites will always equal distance. They will always be the same. 13, 13, 9.5, 9.5. Okay? And so when we use the mean as a balance point, you're looking to make sure that they're balanced. If they're not balanced, then you haven't found the mean. Okay? So it's really, really important that in order to have the mean be absolutely correct, your both sides have to be equal. Okay? All right, so going back, today we will learn how to use the mean as the balance point to compare all the other data points in the data set, which is what we did. They have to be balanced in order to compare them. How do you compare a data point to the mean? You actually count the distance away from the mean. So how far did you go? What does the comparison tell you? The comparison tells you whether you found the mean correctly or not because it is your balance point. It makes it equal on both sides of the mean. Okay? All right, kiddos, that's all I have for you today. Talk to you soon. Bye.